Welcome to lesson 6, which is the final lesson of chapter 3, Pure Mathematics, year 2. And this is all about functions. And today we're going to be looking at transformations in combination of the modulus of f of x and f modulus of x. This is the idea that we introduced earlier in the chapter. And we're also going to bring in the idea of domain and range as well. And then we'll be solving a range of problems involving the modulus function. Okay, please pause the video, have a go at the 4 warm-up questions, and then we can go through the solutions. Okay, let's have a look at question 1. Okay, so first of all, we've got a function f of x, which we need to sketch, and then we also need to sketch g of x on the same axes. So if we look at f of x, we have the modulus of x with 3 added on. So if we consider the modulus of x as the parent function, and then if we add 3, this is a vertical translation of 3 units. So as long as we know what the parent function looks like, this shouldn't be too difficult. So I'll put it on the axes, and I'll do this in blue. So we've got a gradient for the negative branch of -1. So it's going to come in something like that. And then the positive branch will have a gradient of 1. So they will actually be perpendicular in this instance, though not always, of course. So we will label this as y equals f of x. Okay, and then we also have a y-intercept at 0, 3. Okay, and that will do for our sketch. We've got the modulus of x plus 3. So it's just translation of the modulus of x. Now for function g, it's a slightly different story. We've got x plus 3 with the modulus applied to it. And there's various ways of considering this. We could consider, first of all, the graph of y equals x plus 3. And then once we apply the modulus function, anything that is negative, so any y values that are negative, will be instantly reflected in the x-axis and made positive. So if I draw that, we think of it in those terms, the x plus 3 is actually the same as the positive branch of f of x. Okay, so if I just indicate here, this is x plus 3 here, and I should put y equals x plus 3. So they actually coincide, provided x is greater than or equal to 0. So if I put that over the top, it's going to do something like this. So this is y equals x plus 3. And if I take the modulus of the whole thing, we're going to have this situation. Okay, and they haven't quite met up, but never mind. So let's label that. So this is y is equal to g of x. So that's an interesting situation we've got there. We've got an overlay of one graph over another, but it's only partial, and it seems to only occur when we're in the positive x-axis. Okay, but in the for negative x values, there is a clear distinction between the two functions. Now this links nicely with question 2. So it says use your sketch in question 1 and solve the equation. So what would happen if we set these two equations equal to each other? Well, what we've got to be clear about is what the sketch is telling us and how we interpret our answer. Because if we just go blind into this and say, well, normally, I would just consider what would happen when we have the two positive branches intersecting. So what would happen if I set x plus 3 equal to x plus 3? Now, that's a self-cancelling statement, isn't it? That they are literally the same, okay, the positive branches. But these branches are only defined for x greater than or equal to 0, okay? So we'll just state that. So they are exactly the same for x greater than or equal to 0. Now, you can see from the sketch as well, there is no point of intersection between the two negative branches. But there is a point of intersection between the negative branch of f, which I'll just highlight here, and the positive branch of g. So if we try and solve that, what happens? Well, if I take the negative branch of f, that's simply going to be minus x plus 3. Okay, so I consider the part that is modulus as minus x, and that would just simply be equal to the positive branch of g, which is x plus 3. Okay, now here we have something we can actually solve. If we add x to both sides and subtract 3, so we basically get x is equal to 0. And that gives us this unique point right here where they both coincide. So the only way this is going to happen is if x is greater than or equal to 0. Okay, so that's what happens when we solve that equation. We actually get an inequality. It's true for all x greater than or equal to 0. Now we're going to move on to question 2b, and we have to solve the inequality. Now for the inequality, we just look for when x plus 3 in the modulus form is strictly less than 1. If you want to make an addition to your sketch, this is probably a good idea. So we can see the y-intercept is at 3, and I didn't actually put the x-intercept on, but never mind. So at 1, there'll be maybe a straight line y equals 1 going across there like that. Okay, and we can see from the sketch, and sketching is really important in this topic, we have 2 points of intersection, which we can just read off. Okay, and I'll put the x-intercept on as well. So because it was x plus 3, this is obviously going to be at minus 3 right there. So we just solve the inequality. We know there's 2 solutions, so we consider the negative branch and the positive branch. So for the negative branch, we simply reverse the signs of everything inside the modulus. So it's going to be negative x, subtract 3. When is that strictly less than 1? Okay, and we rearrange it. And then for the positive branch, we take the positive form of the modulus, which is just x plus 3, and we solve this inequality. So we do them separately. So if I add 3 to both sides for the negative branch, okay, so I get negative x is strictly less than 4. Now, because of the way I've done this, I'm having to divide by a negative 1 or multiply by negative 1. It's the same process, essentially. This is going to reverse the sign of my inequality. So we have to be really mindful of that. This is going to have to change. So let's do that. So we're going to have x is going to be greater than minus 4. Okay, and for the positive branch, we're going to have x is strictly less than 1 subtract 3, which is minus 2. Now we'll just check this and make sure it makes sense. Remember, we're interested in the modulus being strictly less than 1. Now, graphically, the part where the modulus is strictly less than 1 is right here. So it's this region here. And what we've just done is we've just found those 2 key points. We found the points minus 4, which would be right here, and minus 2, which would be there. These points right here where the arrows are. So this seems to make sense. If x is greater than minus 4, then we know that the modulus of x plus 3 is strictly less than 1. But also, this relationship ends when we get to x is equal to negative 2. Okay, so we have an interval, and we can put these both together and say the following statement. So as long as x is greater than negative 4, but less than negative 2, this is a true statement. Now for question 3, we have to sketch a modulus function, the modulus of g of x. Now, interestingly, g of x itself looks like a modulus function that's been translated somehow. So to take the modulus of what looks like a modulus function, we apply that rule that we met way back in the first lesson, whereby the modulus makes any negative values instantly positive, and it's a reflection in the x-axis. So let's just label the x and y axes first and the origin. Okay, and to complete our sketch, we simply have to identify the regions where the graph is indeed negative. So negative meaning in the y direction. So all this section of the graph for that interval of x is negative, okay, because it's below the x-axis. Okay, so this is a negative region. This has to be instantly made positive by reflecting in the x-axis. So to do this, try and do it really accurately. I'll use a straight line function here. So it makes a W shape. And to complete the sketch, of course, the two branches here are going to remain the same, although I didn't actually overlay that very well. Okay, and we can label that as y is equal to the modulus of g of x. Okay, there's nothing more to say about it. We don't know any more details, but that's how to do it. Now, moving on to question 4, we have a new function h, and it's an exponential function, and we have to find the inverse function. I'm going to keep saying this over and over again. Please make sure you know the distinction between h to the -1 and the derivative. Okay, it's a common mistake where I've seen students find the derivative rather than actually the inverse function. So please be mindful of that. So let's just write it out. So we've got h of x is equal to e to the 0.5 x plus 1. First thing I'd like to do is write it in this form. So we're going to say y is equal to e to the 0.5 x plus 1. And in an exam, this could be a show that, or there'll be some elements of the question which will give you an idea of how they want you to write it. So there might be some missing constants that you have to find. But because there's not a particular form here, we'll just go through the steps. Okay, now the first step, of course, is we need to swap the variables. Okay, now I've written it as y is equal to the function h of x. We swap the variables around. So my y variable is going to become x, and my x variable is going to become y. So I'll just show that in a different color so you can see it. Okay, we did this recently. Now, the next part is we're going to make y the subject. So now, okay, I'll put now, make y the subject. And this will give us our inverse function, which has lots of unique properties, which we'll talk about momentarily. So we'll just get the function itself first. So let's think about how to rearrange this. Well, the first thing I need to do is, because y is trapped in the power here, the first one of the key rules or principles of rearranging equations is to make sure you get the term with the letter that you want as the subject on its own first. So it doesn't matter that the y value is trapped inside that power. That doesn't matter. We need to get that term which contains y on its own first. So I'm forced now to subtract 1 from both sides in order to get close to that step. So if I subtract 1, I'm going to get e to the 0.5 y. Okay. Now I'm in a position where I can release y from that power. Now the way to do that, of course, is to use the inverse operation of exponentiation, which is, of course, logarithms. So I'm going to take the natural log of both sides. And another key thing here you need to be mindful of is when you're taking the log, you do it to the entirety of the left side and the entirety of the right side. Okay, so you do not take the log of x, subtract the log of 1. It's not like differentiation. It's the log of the whole of the left-hand side, okay, is equal to the log of the whole of the right-hand side. Okay, please remember that. Okay, so now we can apply our laws of logarithms. There's nothing I can say on the left-hand side. There's no law of logs that deals with this. So we're just going to maintain the log of x subtract 1. But on the right, I've got a nice feature or a nice principle I can use here. The power, because I'm taking a log, can now be brought down as a coefficient. So this is going to be 0.5 y multiplied by the natural log of e. Okay, and now we have another principle we can use, the natural log of e, which I hope you all know. If you don't know, you can just type it into your calculator, but this is just 1. They are inverse of each other. So now we have 0.5y. If we divide by 0.5, which is essentially the same as multiplying by 2, we get the following. So we get 2 ln of x subtract 1 is equal to y, which is our inverse function. So I'm going to state it to finish this off like so. So h to the minus 1 of x is equal to 2 multiplied by the natural log of x subtract 1. You could also, if you wanted to, because we've got a coefficient at the front, we can use the power law in reverse. So if you wanted to, you don't have to do this because it's not specified, but you can also write this as the natural log of x subtract 1 to the power 2. Okay, they're both the same statement. Right, now the thing we haven't covered is the domain and range. Okay, now the key thing here is the property about inverse functions. Okay, we have the domain of our function h, because that's talking about the x values. Those are the x values we're allowed to put in. That instantly becomes the range of my inverse function. So I know that my y values for my inverse function correspond to the x values of my original function. So I know my y values are going to be any real number. Okay, so that's the first thing. We get that one for free, which is good. Now, to get the domain of my inverse function, i.e. the x values I'm allowed to put in, you can either work on the inverse function itself, now you've got it, and try and figure out what the domain would be, or you can go back to the original function right here and try and figure out what the range of this function is. So I'm going to do that. So if we look at h and we consider what it looks like, so I'm just going to do a little sketch of it. Okay, so it's e to the 0.5 x, first of all. Now, if we think about that, e to the 0.5 x is just going to be an exponential function like so, and it's going to pass through 0, 1. If you put x equals 0 in, you get e to the 0, which is 1. And the fact it's 0.5, that's a horizontal stretch, okay, scale factor 2. So it doesn't really affect your sketch if you're just looking for a quick demonstration of the range. But what we do need to consider is what happens when we add 1. So this whole function is now going to be shifted up by 1 unit. Okay, so will it let me do that? I'm just going to undo what I've just done. So let's shift it all up by 1 unit. So it's actually going to do something like this. Okay, so the y-intercept is now going to be at 2. And that horizontal asymptote that I didn't actually mention, but you should know about anyway, has also been shifted up by 1 unit. Okay, so it was at y equals 0. It's now at y equals 1. So this gives us the range. So clearly the range is just going to be all the values that are greater than 1. So we can write that down as our range for h, which I'm going to do now. And y is also a real number as well, but there's a restriction on it. Okay, and that's the range. Okay. Now, because we've done that, obviously that corresponds to the domain of your inverse function. So I can now say that x has to be greater than 1, where x is a real number, and this is my domain. Okay, if you want to, as an exercise, you can verify that by trying to sketch the log function that we've got here and show that the domain does indeed start at 1 but not inclusive, and then all values greater than 1. Okay, but I'll leave that for you to check. Okay, so that concludes the warm-up. Okay, let's have a look at the worked examples. So we're going to apply our knowledge of modulus functions and transformations of the modulus functions to solve some problems. So in this instance, we've got a function f, and it's defined as shown, where it's got several transformations applied to a parent function, maybe the modulus of x, and we've got to sketch this and state its range. Now, in order to sketch this, I've obviously provided the axes and you've got space to do the sketch, but we might need to build up towards the final sketch in a few steps. So it all depends on how comfortable you are with sketching transformations. Initially, let's start off with the modulus of x subtract 5. Okay, now there is a transformation there, but I think that's a good place to start. So if we just sketch that, let's see what happens. Just do some smaller sketches up at the top here. Right, so we've got the modulus of x. Now the modulus of x is standard, it's gradient 1. It bounces off, in inverted commas, off the origin. But if we translate that by 5 units with x subtract 5, it behaves in the same way as any other transformation. It's going to be shifted by 5 units to the right. So we can keep track of those points of intersection all the way. So it's going to be cutting at 5 on both the x and y axes. So that would be the first step. Perhaps you might want to do a preliminary step, but I think that's a good place to start. The modulus of x subtract 5 right there. Then we need to multiply this modulus function by 3, and that would give us the vertical stretch that we require. So if I put another sketch in here, like so, the vertical stretch, so the scale is going to be shifted slightly in this situation. It's going to become steeper, like that. And think about what will happen to the x and y coordinates. Well, if I'm sketching y equals 3 multiplied by the modulus of x subtract 5, we know from experience that the x values are not going to be affected by this because it's a y transformation. Simply stretching all the y values scale factor 3, so that makes it pretty clear that we're still going to have our minimum point at 5, 0, but our y-intercept is now going to be at 15. We have to triple all the y values, okay, and it's a steeper graph. And I think now we're ready to draw our final sketch. So the final function f of x obviously has this subtract 2, which again is going to affect the y values. Now it's simply going to move the whole graph down by 2 units. So on my large axes that I've got here that I prepared, we're going to put the sketch on there. So again, I'll do it in blue. So it's going to be a steep, or relatively steep, straight line graph for the first negative branch. And then we're going to have the same mirror image of that with the positive gradient right there. And then we can just label all our key points. So if you'll note, the minimum value is still when x is 5. Okay. Now, if we drop down by 2 units, clearly in our second sketch, we had a minimum point actually on the x-axis. So if that's shifted down by 2, which is right here, this is going to be at -2. So I hope this is relatively self-explanatory, really, just from by looking at it. I'm not too interested in where the graph crosses the x-axis. We'll leave that for now. But I am quite interested in where the y-intercept will be. So again, going back to our second sketch, we've got a y-intercept at 15. That needs to be reduced by 2 units. So right here, I'm going to put in 13 as my y-intercept. Okay, and now we can label this as follows. So this is going to be y is equal to f of x. And if you want to be a bit more detailed, we can put in the whole thing. So f of x, which is of course 3 multiplied by the modulus of x subtract 5 subtract 2. Okay, and this is defined for all real numbers. Okay, now for the next part, we're going to solve an equation. Now we have f of x is equal to 1/2 x plus 1. That's not to say that the function is defined as that, because that's not what the question says. Okay, the function f is defined in the first part before we even get to part A. It's defined as that modulus function that we've just sketched. This is simply setting f of x equal to 1/2 x plus 1. So we'll write the first step right here. So this is basically saying 3 modulus of x subtract 5 subtract 2 is equal to 1/2 x plus 1. We've got to solve that, and we've got a sketch waiting to be used. So let's have a think at what 1/2 x plus 1 would look like. So if I sketch that graph on here, so I'm going to sketch y is equal to 1/2 x plus 1, and this is for part B, of course. Well, we've got a lot of information. We've got a gradient of 3 on our f of x and -3. So this is going to be nowhere near as steep, essentially. So a gradient of 1/2, by contrast, is going to be a very, very steady, slow increase. And then the plus 1 is the y-intercept. So I'm going to add that onto my diagram, and we can just do it like so. So it's going to go something like this. Okay, maybe slightly exaggerated, but that's all right. So this is going to be y is equal to 1/2 x plus 1. Okay, now the reason we sketch this as part of the solving the equation process is we can determine how many solutions we expect to find. Now clearly, 1/2 x plus 1, which cuts the y-axis at 1 and has an x-intercept over here, which I could label. So if we set that all equal to 0, this is going to be at -2. We can see that there are definitely, without hesitation, that there are definitely going to be 2 solutions to this equation. It's intersecting the negative branch here and the positive branch. So we can now set up 2 equations. So I'll do that on the line section. You've got a little bit more space than I have, so use your space carefully. So for the negative branch, we'll start with that. And this is not strictly correct terminology. It's just to help you explain, or help me explain what I'm trying to do here. So the negative branch is in this part here. We'll call this the positive branch over there. We need the equation of that negative branch in terms we understand. So the negative branch, we can replace the modulus provided we take the negative version of everything that's inside the modulus, because obviously the modulus makes everything positive. So if all that was negative, that would be negated, if that's the right word, or made positive by the modulus function. So the negative branch must be the negative version of everything that is inside that modulus function there. So I'm going to change it all to -x plus 5. You simply have to just change the signs of everything inside the modulus. So positive x becomes -x, and -5 becomes +5. Okay, and that's for the negative branch. Okay, we'll talk about the positive branch in a minute. And we set all that equal to 1/2 x plus 1. Okay, now a good thing to, we'll clear that the 2 in the denominator first of all. So we're going to have 6 multiplied by negative x plus 5 is equal to x plus 2, just so multiply everything by 2. And if we expand and simplify, notice we're getting onto GCSE work now. 6 times 5 is 30, is equal to x plus 2. Okay, we're going to collect everything together. I'm going to put the x's on the right and the constants on the left. So this is going to be, this is going to be 28 is equal to 7x. Oh, I've just realized I've made a mistake. Let me just undo this. You might have been screaming at the screen. Okay, so I forgot the negative 2. Sorry about that. It's equal to a half x plus 1. Okay, let's try that again. So again, I think I'm going to add the 2 first of all. So that's going to equal 1/2 x plus 3. Okay, let's multiply everything by 2. So that's going to be 6 minus x plus 5 is equal to x plus 6. So that's doubling everything. Okay, again, expand and simplify. Let's try this again. Okay, and collect all the like terms. So we're going to have 24 is equal to 7x. So x is 24 over 7, which is about 3.4, I think. Which is roughly equal to 3.43. We'll do to 3 significant figures. There's nothing specified in the question, so we will round it to that. So there's our answer. So x, that's the first point of intersection. And as you can probably tell from the diagram, it's going to be this point here, just because there is a minimum point at 5, so that would be a 3.43 right there. So now we need to find the other point of intersection on the positive branch. So I'm just going to erase this because I hope that makes sense, and I apologize for the mistake. So going back to the positive branch, and we'll try and do this correctly first time. So the positive branch, everything inside the modulus remains as it is. Okay, and we can change the modulus to brackets. Okay, so this time we're going to have 3 lots of, and it's just going to remain as x subtract 5. We don't change the signs this time. Okay, and I won't forget the subtract 2 this time either, is equal to 1/2 x plus 1. And again, I'm going to add the 2 to both sides, first of all. 1/2 x plus 3. I'm going to double everything. Okay, and then we expand and simplify. So 6x subtract 30 is equal to x plus 6. I'm going to collect the x's on the left this time. So we're going to subtract x from both sides, and we're going to add 30 to both sides. So this is 36. And if I divide it by 10, that'd be 3.6. I don't do that. I divide by 10 and then double it. So that's going to be 6.4. No, it's not. It's not 6.4. Sorry. It's 7.2. If you double 36, you do not get 64. There we go. So that gives us the second point of intersection, which is right here on the graph. So that'll be at 7.2. Okay. So that's it. So the idea behind solving modulus equations is you set up the equation, but you use the sketch to identify the number of solutions. If your sketch is good, it will be clear and obvious what you need to do. And then to do the two equations, you can remove the modulus function, and for the positive branch, i.e. the branch that is not having negatives removed, essentially, you just keep everything inside the modulus the same. And for the negative branch, you have to change the sign of everything inside the modulus, but then you can replace the modulus with brackets and solve as normal. So that's that. Now for part C, it just says explain why f does not have an inverse. Well, remember the properties of inverse functions. For a function to have an inverse, it has to be 1-to-1. Okay, so we can just state that first of all. Inverse functions, or I should maybe not state it like that. Not doing very well with this example. So for a function to have an inverse, it must be 1-to-1, as in a 1-to-1 mapping. Now, if you look at our function f defined for all real numbers, if we restricted this domain here, we could force it to be 1-to-1. But as you can see clearly, if I take, you can do the ruler test as well if you want to, but if I take any horizontal line and put it over the sketch like that, you can see that if you read off, you're going to have two solutions. Okay, so this is what we call a many-to-one mapping, because if there's two solutions to the equation when you draw a horizontal line, that means that two x values map to the same y value. So you can say that explicitly. We can see that f is a many-to-one, and it's the same with a quadratic as well. They're also many-to-one. It's a many-to-one mapping. Therefore, it doesn't have an inverse. Okay. All right. So I hope that makes some kind of sense, and we've got another worked example to have a look at now. Okay, so this is the second and final example for solving modulus problems. Now, we've got a rather complicated looking function g this time, and I'll just say this now. This is a very typical kind of function that they will provide in exam situations. It's rather complicated, but if we build up the sketch gradually, as I'm going to do, I'm going to do it in 3 preliminary stages, and then with the final sketch. Hopefully you can see that it isn't actually too bad to build up a sketch like this, even though there are at least 3 noticeable transformations. So what I'm going to start off with here is we have to sketch this g function, and a good place to start, if you don't want to start with the parent function as y equals the modulus of x, we can skip a step in that sense. We can start with the modulus of x subtract 3. Okay, so for the first sketch, we're going to have a look at y is equal to the modulus of x subtract 3. Okay, and I'm going to work outwards. Now, if we draw that, obviously this is a translation in the x direction. And what I strongly recommend you do, especially in this situation, and you'll see why, is keep careful track of the minimum values and the y-intercepts. So x subtract 3 is going to look something like this. The gradients are perpendicular because it's a gradient of 1. And we can hopefully deduce very quickly that we're going to have an x-intercept at 3 and a y-intercept also at 3. So that's the first stage. So we've dealt with the modulus part straight away. The next thing I'm going to do is I'm going to multiply all the y values by 2. And that's because I'm going to deal with this part of the transformation, the 2. I'm going to deal with the negative part separately. So if we consider next the doubling of the y values, so in other words, y is equal to twice the modulus of x subtract 3, we simply have to double all the y values, and this is a vertical stretch. So just to give a sense of scale, I'm just going to sort of draw it like this. So the gradient becomes steeper on both sides. We're still going to have the minimum point when x equals 3 because this transformation does not affect the x coordinates, but now we're going to have a y-intercept at 6. So notice how the y-intercepts have doubled from here to here. Okay, and that's because of the 2. All right, now we can add this negative part. So the negative part, if we now consider what happens when we multiply everything by a -1. Well, again, it's a transformation you're familiar with. Everything gets flipped in the x-axis because the negative sign will change the sign of everything. And everything at the moment is positive in step 2. But in step 3, everything is going to become negative. So if I add that to this sketch now, it's going to be something like this. Notice the x-intercept is still not affected. Okay, it's still at 3, but now we have a y-intercept at -6. Okay, now notice as well, I'm keeping careful tabs on these intercepts. It's really important that we do that. So we have the -6 there because of that negative. Right, now we're going to draw the final thing. And you'll probably see why I said keep close tabs on these minimum points and the y-intercept. Now the reason is we're now going to add 6. And if we add 6, again, that's a y transformation. In fact, more specifically, it's a y translation, which means I add 6 units to all the y values. If I do that, you'll notice what happens. So if we go back to sketch 3, first of all, by adding 6 to the y values, that y-intercept is going to shift up by 6 units, and it's now going to intersect at the origin. So let's draw the final sketch now. So it's going to be a relatively steep gradient compared to sketch number 1. It's going to pass through the origin and something like that. And we can now label all these key points. We know the maximum point now is going to be at the point 3, and it was at 0. It's now going to be shifted up to 6. Let's rewrite that 6. Okay, the y-intercept is now the origin, which I'm going to label now. So that's just the origin, and this is the y-axis. This is the x-axis. And there we have our sketch. Now, if you wanted to, you could also find the other x-intercept right here. But I'll leave that up to you if you want to do that. Just set the positive branch equal to 0, and then you can solve it. Now, it says we have to state the range. Now, if you look closely at the sketch, again, keeping tabs and everything is really handy for this. The range is clearly going to be everything. The function is defined everywhere as long as it is less than or equal to 6. So the range is pretty straightforward in that sense. So use your sketch to determine the range. Less than or equal to 6, and obviously y is going to be any real number, simply because we can put in any real number for x, so that has to correspond. Right, now for so that was part A, broken down into 4 stages. Now for part B, we're going to solve an inequality, but again, we're going to use our sketch. So for part B, g of x, when is g of x strictly greater than 4? Well, we just add the line y equals 4, and we'll have a couple of equations to solve, I'm predicting. So if I put that on here, well, the maximum is at 6. So if I put 4 round about there, we have y equals 4. So we have a narrow range of values whereby our graph is actually greater than 4. It's only in this small interval. So the task now is to figure out what the x interval is by determining the 2 points of intersection here and here, and we'll be able to read them off essentially. So I want to find out what that point is. So it's going to be slightly less than 3, and that one is also going to be slightly greater than 3. And common sense tells you they should be the same distance from 3 because of the symmetry of the graph. But let's solve it algebraically first, and we can talk about it later. Now, I'm going to call this branch the negative branch again, although it has a positive gradient, and this one the positive branch, just for consistency. Okay, so let's have a look at the negative branch first. So remember, for the negative branch, everything inside the modulus has its sign changed. So we can set up an inequality as follows. So we're going to have 6 subtract 2 multiplied by the modulus of x minus 3, and we're interested in when that is greater than 4. Well, for the negative branch, all I have to do is replace the modulus with brackets, and I change the sign of everything inside it. So that's going to be minus x plus 3. And this is going to be greater than 4. And I solve that. So let's do it. Multiply out the bracket first. So we're going to have 6 plus 2x. Subtract 6 is greater than 4. So therefore 2x is going to be greater than. Now you'll notice the 6's will cancel out on the left-hand side, which is very handy. So that cancels with that. So we're just going to be left with a 4 on the right-hand side. So in other words, x has to be greater than 2. And does this make sense when we look at our sketch? Well, if I add it on here, if this is 2, we can predict now that the second intercept is going to be at 4, but I just want to verify that algebraically in a moment. So is this going to be at 4? Because by symmetry, it probably should be. Also, we know it makes sense. It's got to be less than 3, but greater than 0. So it fits all the criteria, and it looks like it's going to be correct. So now let's test the positive branch and just verify that. So for the positive branch, and like I said in the previous example, this is not technically the right terminology, but it's just so I know whether I'm changing the signs or not inside the modulus. So we've got 6 subtract 2. Now I can put brackets in here, but I just keep everything as it was inside the modulus. So x subtract 2. No, sorry, nearly made a mistake again. X subtract 3. Okay, which is greater than 4. Okay, let's expand and simplify. So we have 6 subtract 2x plus 6 is greater than 4. Okay. I'm going to add the 6's together. Well, we can collect all the numbers together. If I add the 6's together, that's 12. And then if I subtract 4 from both sides, that of course is going to give me 8. And then if I add 2x to both sides, that's going to give me 2x here. Okay, you can do this however you wish. Divide by 2. And we have x is strictly less than 4. So I've just confirmed that that is indeed at 4, as we anticipated. So at this point here, that's correct. So that's good news. We know the distance between each of these must be 1 by symmetry. And we've also got the interval. So we can state the interval now, because it's got to be between these two values. So my interval, putting all this together, is simply going to be x values that are greater than 2, strictly greater than 2, but less than 4. Okay. So that's the final answer. That concludes the lesson. That also concludes this chapter 3 on functions. Okay, thank you. And please try the exercises. It's really worth getting stuck into some of those questions. They are quite like what the exams put forward.